welcome to our first tutorial this afternoon. Our speaker is Alan Neuringer, and the title of his talk is Variability of the Operant. So a subtitle of this talk could be something like everything you want to know about variability, not the other thing, but we're afraid to ask. Alan Neuringer got his degree at Columbia University around 1962, and he likes to say that one of his first teachers was Fred Keller. And then he worked with Tony Nevin, who taught him to program relays. And then he moved to Harvard and worked with Dick Ernstein, and then many of the colleagues that some of them are here, but that you all know: Howard Franklin, Billy Baum, Phil Heinlein, John Stadden, Fantino, Ben Williams, and many more. Then he moved to Foundation for Research on the Nervous System, and since about 1970s, I think, he's a faculty member at Reed College. He lives in Oregon. And he has done a lot of research in a variety of topics, from superstition to preference to choice. Consistent with the topic of his talk, he varied a great deal. In the last 20 years or so, Alan has concentrated on the study of variability of the operant. And this is quite interesting work, as I'm sure you will agree by the end of this talk, because one of the criticisms of research in this area is that many times it portrays animals as machines, or machine-like, and so only emphasizes the repetitive, stereotypical, automatic sorts of behaviors. I like to reply in two ways to this sort of criticism. First, as you will see by the end of the talk, it ain't true. Second, it is as if the people making these sort of remarks had much more to say about this topic, this complex topic. Most of the time it's not true either. They don't have much to say about the complex topic of variability, of creativity, improvisation, flexibility, plasticity. So what I like particularly about Alan's work on variability is, first of all, the range of questions he asks are interesting questions. Second, the methodology is driven by the problems, and unfortunately, like so many times happens in this field, it's not the other. Fortunately, it's not the other way around. And third, you will see that there is an effort to integrate a wide range of phenomena that converge on the same topic. Try to understand under what conditions the animal and the human also can maintain, even increase its level of variation when its behavior becomes more plastic, more flexible. What's the function? What are the consequences of this? Under what conditions you get? And I'm not sure this is all there is to creativity, but I do know that is at least a necessary condition, because if behavior is highly stereotypical, rigid, automatic, quite predictable, it's anything but creative. So without further ado, please welcome our next speaker, Alan Neuringer.
Thanks, Armando. I'm going to see if I could use this mic. So, what do we mean by voluntary? Before the talk began, I said to Armando, I think this might be the most difficult talk I've ever given, and I'm a bit afraid of it. I need your help, because I'm going to be dealing with that question: what does voluntary really mean? And you could start helping me by moving your index finger up and down and thinking about what the heck is going on. What's the difference between moving your finger up and down and if I were to come and move it for you? What's the difference between your moving it up and if you had put it down and something suddenly pricked your finger, or a little shock and you pulled it up, or if it was a conditioned response? What, in fact, is the difference between voluntary and involuntary behavior? It seems to me to answer questions like that, we need to use every means possible. including observations of our own behaviors. Joshua Lederberg, a Nobel Prize-winning biologist, once wrote, "One needs the ability to imagine oneself inside a biological situation." I, Lederberg, had to think, what would it be like if I were one of the chemical pieces in a bacterial chromosome? And I had to try to understand what my environment, intracell environment was. I had to try to know where I was in the cell. I tried to know when I was supposed to function in a certain way and so forth. And you're well aware of Einstein imagining himself on a moving body as it approached the speed of light as opposed to another body. We could do no worse than using this kind of imagination when dealing with some of our own problems. We should not be afraid to try to get inside of the organism, trying to see what's going on. What do we mean by voluntary? Descartes offered one possibility. Voluntary comes from something extra-physical through the pineal gland. At the other extreme, we have Laplace and Newton, who in essence believe that there is no voluntary. It's a word, but everything is completely determined. So at its very deep level, there is no difference between the unconditioned or conditioned reflex and the voluntary operant. I reject both of these positions. I reject Descartes because it is empirically unsupported and untestable. I reject Laplace, as did, I believe, B.F. Skinner and probably many of you, because it ignores an important distinction: respondent versus operant, voluntary versus involuntary, emitted versus elicited. But having said those words, what is the distinction? What does it mean? Skinner suggested that operant responses have three defining characteristics, and that these characteristics capture the meaning of voluntary. First, operants are controlled by reinforcers, selected by consequences. Second, operants are controlled by discriminative stimuli, events which occur prior to the operant and set the occasion for it. Third, operant responses are members of a class of functionally equivalent instances, the generic class. Let's briefly explore each of these. Operants are reinforced. If a lever press response is followed by pellets repeatedly in the rat comes to respond persistently on the lever. The reinforcement history explains the behavior. We might also say that the rat presses the lever because he expects a reinforcing pellet to follow the press. Voluntary behaviors also are explained by their consequences, both experienced and anticipated. Why did you go to that particular restaurant? Well, because I had previous good experiences there. Or because I anticipate having a good, or want a good meal. Why did you do one thing rather than the other? In order to overcome. There's always that kind of reason that you can apply to your voluntary actions. But reinforcing consequences will not alone explain the voluntary act. There are many other cases of selection by consequences that most of us would not classify as either operant or voluntary. The most notable example is evolution. It works via selection by consequences. Another example is how the immune system changes. I could give you many other examples. I won't go into detail. But there are many other phenomena that don't capture what it is we at least intuit as a voluntary response. Well, perhaps adding discriminative control will help. The rat presses the lever only when an overhead light is illuminated, the light serving as a discriminative stimulus. Voluntary behaviors can similarly be explained. Why did you decide to eat the Frankfurter? Well, because the smell wafting from the stand suddenly motivated me to. Why did you ask that attractive person for his or her telephone number? Well, because the attraction was immediate and it made me think, etc., etc. But discriminative control also has its problems. Thorndike hypothesized discriminative control. There are many other connectionist theories in which you have a stimulus. If the stimulus is followed by a response, and the response produces a reinforcer, then the hypothesis is there's a strengthening of the bond between stimulus-response. And with added reinforcement, you have greater strength such that eventually given stimulus, then response. Note the similarity between Thorndike's view of operant-type behavior and the Pavlovian conditioned response. In both cases, you have a stimulus that compels or obliges a response to follow. The Thorndike view did not seem correct to Skinner, nor to most of us. The operant appears not to be elicited by a stimulus in the same way that a Pavlovian response is. Operants differ from respondents, we think, in that respondents are elicited, whereas the operant is emitted. I take that distinction to be profoundly real. But what does it mean? Perhaps the generic nature, the generic class in which the operant exists, maybe that will help us. The operant class is composed of many instances, and the instances are often topographically different, but they all serve the same function. The example we all know of is a lever press. The rat could press this way or that way or with its mouth. As long as the micro switch goes down, it's an effective response. And the way Skinner analyzed the behavior was at the level of the generic. He looked only at microswitch closures. Analysis at the level of generic class have provided us with very orderly relationships, and such analyses are certainly worthwhile. The generic class also introduces the notion of probabilistic instances. Let's go back to the lever press. According to Skinner, we could not predict exactly how the rat is going to press. We do understand something about the press and its class, but we don't know left paw versus right paw. We don't know about the instances, and in fact, he thought they were occurring probabilistically. Put simply, whereas the observer can predict that the rat will press the lever, the exact way of pressing is less predictable. Might it be just this probability that makes people think that they can exert voluntary control? Is that what the insight is? No. The probabilistic nature of the operant will not alone suffice. We don't think of the outcome of a throw of dice as voluntary, or a toss of a coin as voluntary, or the occurrence of an atomic particle being emitted as voluntary. There is something special about the generic operant, however, that might help us to disentangle this voluntary conundrum. Within-class probabilities are controlled in a rather unique way by reinforcement contingencies. That is, the uncertainty of operant responses is readily manipulable, decreased or increased. Stated another way, the variability of operant responses can be reinforced. Stated yet a different way, variability is an operant dimension of behavior. I will review some of the evidence and then return to a consideration of what this tells us about voluntary action. Research begins with Karen Pryor's work on porpoises, about which I'm sure many of you know. And what Pryor did, it's indicated by this slide, is reinforce porpoises for different types of flips and jumps and moves. Every time a session began, they had to do something that she had never observed before, and lo and behold, the porpoises came to emit extraordinarily unique, very previously unobserved behaviors. And the notion was, oh, she was able to reinforce variability. Don Baer and his colleagues, Holman, Getz, took that work and reinforced children for novel block constructions and drawings. These demonstrations are highly influential. But what was needed is a more lab-based way of analyzing what's going on when you presumably try to reinforce variability. What's the phenomenon? Don Blau in the mid-1960s, reinforced pigeons for pecking keys with inter-response times that matched a Poisson distribution. It was like that of an atomic emitter. To the extent that these are the mean number of responses by 3 different pigeons as a function of IRT, inter-response time bins. I'm not going to give you details here. But to the extent that the lines are linear, that's what one would expect from a random process. This is what pigeons did. Barry Schwartz, then Page and Neuringer, and Armando Machado took a slightly different tact. They reinforced pigeons or rats for emitting sequences of responses across 2 levers or 2 keys. And what a number of us found is that in doing this too, one could find highly orderly variable behavior. This is from a paper by Armando. The extent to which the points are approximated by the line indicates this stochasticity, or the probabilisticity, that's not a word, but the randomness of the generation process here. Well, are we really reinforcing variability? Imagine a condition in which a rat has to emit 4 responses across 2 levers. And imagine that you don't reinforce him if he does the same thing over and over again, but you do reinforce him for varying the sequence. Left, left, right, left, okay. Right, 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 left, yeah, you get reinforced. Right, left, left, right, yeah, you get reinforced. Right, left, left, right, little timeout. If you repeat any of the recent, say, sequences, you get a little timeout. If you vary, you get reinforced. Well, rats, in fact, have an easy time, an easy go of this. They learn rapidly to vary. And if you present another rat with exactly the same sequence of reinforcers and timeouts as the experimental animal, so that the frequency of reinforcement is exactly the same, the other rat, he's not stupid. He just goes left, 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 left. Left, 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 and occasionally he gets reinforced, occasionally he gets timeout. That is shown in this slide. To the leftmost point is a group of rats. You don't have to worry about what's on top. It's 2 separate experiments. But a group of rats being reinforced for variability. U value is an index of how variable the animal is. When the animals are being reinforced for varying their performance, their U value, or uncertainty, or variability, is very high. When the same animals are then reinforced exactly as they had been in the previous phase, but independent of variability, i.e. a yoke condition, variability goes down. And then return. Next slide is a single animal reinforced for variability on the left. Yoke goes down, reinforced for variability. The control is exact and precise. These data suggest that it's not frequency of reinforcement. It's not just, oh, I'm not getting reinforced very often, so maybe that's maybe the fact that the animal is not getting reinforced often would explain why it's varying. These data suggest that's not what's going on. But the notion that variability is elicited by lowering reinforcers or elicited by extinction, it's so much in our field that I've studied that question in a variety of ways. The next slide will show you 4 groups of rats, each group being reinforced for a different level of variability. Some rats are reinforced if they go across 2 levers relatively, the contingency is quite permissive. They have to vary just a little bit. The other group's a bit more, the other group's a bit more, and the final group, they had to be highly variable, highly unpredictable in order to get reinforcement. This is research by Alicia Grunow, and the points to the left are for when every time the rats meet the contingency, they're reinforced. U value is along the y-axis. The lowest curve are for rats who don't have to vary very much, and they don't. As the contingency becomes more stringent, more demanding, variability increases. What's going on the x-axis is over phases of the experiment, we decrease frequency of reinforcement. Now, under VI1, only on the average of once a minute for meeting their respective contingencies are they reinforced. Then only on the average of once every 5 minutes. Note, there is a small effect of decreasing reinforcement. Note also that the direction of the effect depends upon what level of variability is being reinforced, something which I don't believe anybody realized before this experiment. And that the effect is relatively minor compared to the contingency effect. The next slide shows the same data. It's hard to see, actually, but these are distributions of individual sequences of responses, the probabilities of individual sequences in the 4 groups. The top graph being a set of graphs showing for the least demanding contingency, and the very bottom, the most demanding contingency. And in each case, each panel, there are actually 3 curves drawn, one for CRF, one for VI1, and one for VI5. You could barely distinguish the 3 curves, but you can tell the difference between the panels. What's going on? Contingencies based on levels of variability precisely control variability, much more so than frequency of reinforcement. This is true in extinction as well. To the left, you see, to the left upper graph, are 2 curves. The closed points are for rats who are being reinforced for varying sequences of responses. And what we see are a probability distribution, the individual relative frequencies or probabilities of individual sequences across all the sequences they can emit. In this case, there's a left lever, a right lever, and a key. You don't have to know the details. The open circles, which you can barely see, I'm sorry, the open circles are what I just said, reinforced for variability. The closed circles are what the animals are doing during extinction. They're superimposed in essence. The distribution of relative frequencies of individual sequences is not dramatically changed. To the right is a rep group. These animals are reinforced for one and only one sequence. Left lever, key, right lever. That's the only way they could get reinforced. Closed circles are reinforcement for that sequence and that alone. Open circles are extinction. Once again, there's a slight effect of extinction, but relatively minor compared to the contingency effect. To understand what the bottom does, you'll have to read the paper. I won't go into it. The important point here is that reinforcement contingencies exert control, precise control over levels of variability. Variability of responses in time, variability across different operanda, variability of what the animal does. Levels of response variability are controlled as well by discriminative stimuli. Imagine the following experiment. In the presence of one overhead light, the only way a rat can get reinforced is left, left, right, right. It's the only way. If it goes left, 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 right, time out. Left, right, 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 time out. Left, left, right, right, pellet. Left, left, right, right, pellet. In the presence of a different overhead light, the only way the animal can get reinforced is by emitting sequences of responses that are highly variable. Left, right, left, left, right, 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 left, 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 right. They learn this, and they learn this well. In a second experiment, we had in one component of a multiple, reinforcement for variability. In the other component, reinforcement yoked to the first component. Animals have to vary in one component. They could do whatever they want in the second. They could keep varying or not. The data show clearly the boxes are levels of variability when stimuli are present, the left set of upper box and lower open circle. The box is when variability is required. The circle is in the yoke component. Levels of variability are significantly different. When we remove the stimuli, everything else exactly the same. variability is the same because the variability is being controlled by the discriminative stimuli. Reintroduce the stimuli, and immediately variability levels change. Control by reinforcement over variability is even more precise than what I've said to this point, sorry. If you say only sequences that will begin with left-left can be reinforced, but the sequences have to vary one from the other, you'll get left-left, right-left, left-left, left-right, left-left, right-right. The animals will learn that contingency. Here's another way in which the precise control over variability was demonstrated. Chris Ross had students draw rectangles on a computer screen. They were given points sometimes, and all they were told was draw rectangles, get as many points as you can. There were two groups. One group was reinforced if the rectangles met 3 simultaneous variability contingencies. The location on the screen of the rectangle had to vary, the area of the rectangle had to vary, and the shape, which is the height divided by the width, the shape of the rectangle had to vary. They had all to vary in order for the points to occur. The poor kids in the other group were yoked to the first group. They were getting reinforced whenever the member of the first group were reinforced. The gray bars show levels of variability for each of these dimensions, area, shape, and location, for the experimental subjects. The dotted bars are levels of variability in the yoked control. This is a total of 300 responses. That's the whole experiment. It happens fast. In the second experiment, what Chris did was, unbeknownst to the subjects, require that one of these dimensions not vary while the other of the 2 dimensions simultaneously vary. That's the only way you could get reinforced. In one group, they had to repeat the area, the same area, over and over again, but shape and location had to vary, etc. The left group, the left set of bars, is for the group in which area had to repeat. The dots show levels of variability in area. U value is relatively low for area, high for shape and location. Without going into details, the subjects well learned. They could not necessarily tell you exactly what was going on, but they met the contingencies. How do they do it? If I asked you to vary your behavior, how would you do it? Well, there is a lot of different mechanisms you could use. If you're a referee in a football game, the mechanism you would use is take out a coin and flip it. That's how to vary. Use some external aid. Another way you could meet a variability contingency is remember what you've done and don't do it. That's how a rat deals with a radial arm maze. It remembers where it's gone down the maze and doesn't repeat, or it remembers where it's not gone, depending upon the particular situation. There's evidence, I believe, as I suggested early on, that there's a third way, and it's most important, I think, for this talk. I refer to it as the stochastic generator competency. It generally gets people upset, but gives the sense of it. Recall the Don Blau and the Armando Machado functions. They showed that animals' performances could be mapped onto a variability generator type process. I did something similarly, perhaps slightly more sophisticated, with human subjects. And the green curve shows for this particular statistic, I won't give you details, the green curve shows for this particular statistic what the distribution would look like for a random generation, for a random process. These are high school students sitting at a computer terminal emitting 100 ones and zeros at a time, 100 responses, and then getting some feedback, and 100 responses, feedback, 100 responses. The red line to the left shows what these kids' distributions looked like at the beginning of the experiment. The right, this is just one subject, by the way. The right box shows green once again for a random generator, and red for the subject. The subjects learned, that was one statistic. This is a second statistic. I could give you 10 of these, I won't. I've done this with as many as 30 different statistics and shown that human subjects learn to match their performance to that of a random process. There's another way we could test whether stochastic processes are going on by comparing it to a memory hypothesis. Think back to rats, left, left, right, right, left, left, right, right, left, left, right, right. That's the only way they're getting reinforced. You tell me, what happens if I slow them down? Left, pause. Left, pause. Right, pause. Right, food. As I increase that pause, what do you think will happen to percentage of correct responses? Go up, stay the same, or go down? Go down. That's exactly right. Now tell me the same prediction for a group of animals that's being reinforced for varying sequences of responses. Left, right, right, left, 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 right, left, pause, right, pause. Increase the pause there. If those animals are using, quotes, memory as the first group is, what should happen to their probability of meeting the contingency? It should go the same direction. It doesn't. Your prediction is correct for left, left, right, right. As you increase inter-response time, performance is degraded. For a group that's being reinforced for variability, performance gets somewhat better as you slow them down. There's a variety of reasons for that. This is a consistent finding for pigeons, for rats, and a number of studies in humans in the cognitive literature finding the exact same thing. Similar experiment. One group of rats. In the presence of one stimulus, left, left, right, right, presence of another stimulus, vary. One stimulus, left, left, right, right, the other stimulus, vary. Then inject 2 grams per kilogram body weight of ethanol. What happens to left, left, right, right to a drunk rat? It goes down. What happens to variability in a drunk rat? Let's say it's a jazzy rat. Left is increasing levels of ethanol. Probability of varying stays exactly the same as you get these animals drunk. Same animals. This is a multiple schedule. Exact same animals, same experiment. Repeat goes, falls apart. The conclusion I come to is that memory is probably not responsible for the ability to vary in these situations. There's other evidence, and I'm actually going to skip through it. But the evidence supports a stochastic generator hypothesis. Some implications of operant variability. First, inability to predict behavior is generally attributed to ignorance of controlling variables. But these results show that highest levels of variability may result from identifiable reinforcers. Second, this demonstrates another way, a powerful way, in which reinforcement principles can be applied. Third, it also suggests applications to some real-world problem areas, and I'll describe those in a moment. And fourth, and perhaps of greatest significance, reinforced variability may help us to explain voluntary action. First, a few applications. We've often said that shaping new operants depends upon a variable substrate, a variable baseline. Where does the variability come from? Well, it's just there. Or we withhold reinforcement and induce it by extinction. Alternative, reinforce it. Rats were required to learn what is for them a very difficult sequence. Hit the right lever, hit the left lever, hit the left lever again, go back and hit the right lever, then go over and hit the left lever. That's the only way you're going to get reinforced. Everything else produces timeout. One group of rats was simply given that requirement, and whenever they emitted it, they got a pellet. Everything else, timeout. Session after session after session. They learned to go to sleep. A second group of rats, in order to maintain motivation, was reinforced concurrently under a variable interval 1-minute schedule for any sequence of 5 responses. Once a minute, whatever they did got a reinforcer. In addition, every time they did left, right, right, left, right, different experiment, right, left, left, right, left, they were reinforced immediately. So it's to their advantage to learn the target sequence, right, left, left, right, left. What did these guys do? Well, they continued to respond. Their motivation was maintained, but they didn't learn. Third group. Again, VI1, but now they're reinforced for varying sequences of responses. Concurrently, every time they do right, left, left, right, left, they get reinforced for it. Oops, that's the one we're skipping. The third group learns the sequence. Only the third group learns the sequence. We've done a number of other studies suggesting that explicit reinforcement of baseline levels of variability facilitates conditioning of complex or difficult to learn responses. Similarly, we've reinforced rats for novel interactions with objects. Put a soup can in their cage and reinforce the rat first for going in the soup can if it does that. Then no longer reinforce for going in. Now the rat has to do something else. It pushes it. Reinforce that. No longer for pushing will you reinforce. It has to do something else. It pulls it. You reinforce that. And you continually reinforce in a session novel interactions with soup cans. Second session, put something else in the chamber. A whole series of wires, and now it has to pull the wires, push the wires. So you're reinforcing these animals for novel interactions with different objects. Second group of animals, next door to the first, exactly the same objects. They get reinforced whenever the first guys get reinforced, yoked. Third group of animals, you lift them up and you hold them and you make nice to them. Test. Put them in a large room with 30 toys on the floor. They've never been in the room before. They've never seen these toys. And hidden in the toys are little pieces of food. In one case, it's a toy truck. In the cab of the truck is a pellet of food. In another case, it's a girl's chest of drawers. You have to open the drawer, and in the drawer is a little piece of food. In the third case is this big, heavy hairbrush. And in the brush, another case, there are these, for kids, these rings that go on a central stick. The rings get smaller, and in between the rings are little pellets of food. I mean, you just put the rat in there for 20 minutes. Who finds the food? The left bar are the animals who had previously been reinforced for novel interactions with objects. They found 17 or 18 pellets in 20 minutes. The other two bars are for the two controls, yoke control and the handle control. Not only didn't they find very many pellets, what was really interesting, they seemed to be more afraid. They stayed along the side of the wall much more. Reinforcement of variability may also help in treatment of some abnormal behaviors in human populations. Neil Miller worked with children diagnosed with autism. And what he had is he created this game with 2 big buttons, and I won't give you the details, but they had to respond variably on the 2 buttons for individual reinforcers. For each child, it was a different reinforcer, but he was able to maintain behavior. First, he reinforced probabilistically, independent of variability. Then he required variability, and he compared them to normal controls. These data show, first, the squares represent the autistic kids. The autistic kids were always less variable than the controls, not unexpected. What's potentially important is contingencies of reinforcement significantly increased their variability. That may be important. A separate study by Jen Hopkinson assessed depression in Reed College students. There's a paper and pencil, and there are a lot of students at Reed who happen to be depressed. And she had them playing a different game in which at first they're reinforced independently of variability, then reinforced for variability. The left points show levels of variability when reinforcement does not depend on the variability. For depressed subjects, significantly lower levels of varying than non-depressed. And the exciting finding here is when you reinforce for variability, they rise to the same level. We have found analogous results in aged versus not aged younger rats. When young versus old rats are reinforced probabilistically, the aged guys don't vary. When they're both reinforced for variability, they come to the same higher levels. There too suggesting one way of dealing with age. How does this all help us to explain voluntary action? Voluntary behaviors have three characteristics. They can be explained. They make sense. A voluntary behavior is done for some reason. Second, they often cannot be predicted. They're not compelled by prior discriminative stimuli. In some sense, they're free. And third, they seem to be under our own control. How can these all be true? How can they be explained, not predicted, and feel free? Let's consider an example. A concert pianist. The concert pianist's behavior is under precise control of the notes on the page. A Beethoven sonata, a Bach fugue, a Ravel, and you say to the concert pianist, play AED, and the concert pianist goes beautifully AED, precisely controlled. The concert pianist at the one and the same time can sit down without notes, without you saying anything, and go, and AED might come out. No stimulus. In the first case, precise control by discriminative stimulus. In the second case, emergence from a class of possible occurrences. Another example. What year is this? 2002, 2002. Precise control, 2002, by this question. 9133826008952002843. 2002 comes as a member of a set of infinite random numbers, just as much as under precise control. Both are true. Language is another obvious case. Words are precisely controlled in competent speakers by discriminative stimuli, contexts, and reinforcers. But the same words can occur much, much less predictably at other times. What is that common red fruit that you eat? It has a stem, it's sometimes green, it's made into pie, it's an apple. But the same word, apple, can emerge, be emitted as a relatively unpredictable member of an increasingly large set of operant responses. If I were to ask you for words beginning with A, you might say auto, Alabama, Argentina, apple. If I were to ask you for any word, you might say man, kiss, both, fear, apple. If I were to ask you do anything, you might do anything, and apple might emerge as the example. Voluntary implies exquisite control over instances, and at the same time, potential for the instances to become members of operant classes, including the class of all possible behaviors, and therefore to be quite unpredictable. The greater the precision of control, the more voluntary. The larger the response class, and the flatter the within-class distribution, within-class probability distribution, also the more voluntary. Both are true. We can start to appreciate the multiple sources of explanation for voluntary behavior. Discriminative stimuli, context, reinforcement contingencies, all enable us sometimes to predict and control instant responses. Yes. These controlling events are part of the explanation of the voluntary act. But sometimes it is the response class that serves to explain. And the larger the class, the less well you could predict the instance. All operants, by their nature, can become members of response classes, generic classes, Skinner called them, and the class provides for and explains the unpredictability. We therefore have explanation, sometimes at the level of instance, and sometimes at the level of generic class. Voluntary responses can be explained and are potentially unpredictable. Red, white, and blue. Red, white, and chocolate pudding. Red, white, and poo-poo, two-poo, goo-poo. The voluntary operant is therefore made possible by the fact that variability is an operant, class size within class probability distributions. And members of a class, these all are modified moment to moment, online, by discriminative stimuli and contingencies of reinforcement. Okay, we've discussed two of the characteristics of the voluntary response. First, the instance can be precisely controlled by a particular discriminative stimulus. The greater the precision of control, the higher the degree of voluntariness, the concert pianist. Second, the instance does not necessarily occur given that stimulus. It could not occur, and may occur absent that stimulus. It may emerge, that may be the better word, from the class, or be emitted. That's what emitted means. As a member of a class of functionally equivalent instances. What about that third characteristic? We think we can control voluntary acts. We can initiate them. Often what is meant is that a decisional activity precedes the overt act. Should I go out for a beer, I think? Should I go out for a beer? I think, I need to study, but on the other hand, and then I decide, yeah, I'm going to go out for a beer and think that's a voluntary response on my part. This type of decisional activity, this, let's see, I'm imaging, I'm saying to myself, I'm considering, I'm thinking the possibilities, this type of decisional internal stuff is what most people mean when they speak of voluntary control. But that won't suffice for two reasons. First, it just moves the problem back one step. What made me ultimately make the decision to go out for a beer? That was a voluntary response. So it's just sort of pushing it back. Equally importantly, the vast majority of our voluntary behavior is not preceded by that sort of thing. Help me again. Move your finger. Let's see, why don't you first decide, think about it. You could move it down, up, zigzag, you could move it around, you could go, you could move. Think about how to move your finger and then move it. Help me. Do it. Okay, some of you are doing that. Okay. Now move it in a variety of ways rather rapidly. Just move it until I tell you to stop. Move it different ways, stop. The very last way you moved. Why'd you do that? What the heck caused that? Did you have no control? Of course you controlled that. Most voluntary behavior is not preceded by conscious thought or decision. Rather, attribution of voluntary comes after the emergence of the instance from a functional class. You moved your finger because I asked for it. Any member of that class satisfies the contingency. You know that. You could have done otherwise, you think, and therefore attribute voluntariness after the fact. Philosophers, religious writers, novelists have been arguing about voluntary action for thousands of years. Democritus and Epicurus, Aristotle, St. Augustine, Spinoza, Dostoevsky, philosophers today and psychologists today. Finally, I believe we can give empirical meaning to what voluntary is all about. Many will not like what we're doing. They didn't like what Copernicus did. We're not at the center. They didn't like what Darwin did. And now an experimental analysis of behavior by B.F. Skinner. Yes, Skinner began this quest. And I'm just following in his immense footsteps. But science is organic, and we grow. Beyond what Fred Skinner knew, beyond what we now know, we can experimentally analyze voluntary action, manipulate it, decipher it, explain it, and thereby come to a deeper understanding of what we are, what we do, and why. Two concluding comments. To students, don't be content with a narrow set of research questions. You can influence the set, its size, the class members, the uniqueness that emerges, And when an interesting problem happens to emerge, treat it as you would a feeble flame, for who knows what advances might follow. And to everyone, we can all influence our own voluntary control. We can vary responses, how we walk, how we look at and interact with others, what we write and how we study and what we study. When you find yourself ruminating, you have some control over the size of the set of ruminations. You have control over the ruminations. Whether it's interactions with loved ones, research topics, classes you're teaching, or patients you're treating, variability is an operant. And by varying levels of variability, you may optimize your voluntary and therefore functional contributions. Thank you. Yeah. Yes.
What is the difference between explaining voluntary behavior and describing voluntary behavior? Repeat the question.
Repeat the question. What is the difference between it? No, I'll do it. What is the difference between explaining and describing voluntary behavior? A complete description may be the best explanation. One could suggest that by going to basic principles, you're increasing the explanatory power. That's what I'm trying to do. I'm trying to take what is an obvious phenomenologic occurrence and trying to analyze it in terms of principles we readily understand. Nothing that I've said by itself should surprise you. Possibly the only surprise is my trying to apply it to this strange thing called voluntary. Yes, Alex.
People working on animal welfare have recently, or several years now, been very interested in the problem of stereotypic behavior. That is exactly the opposite.
Yes.
Of what you described. Can you relate your findings to that problem?
Alex asks about people working on animal welfare issues have noted that high levels of stereotypy, within cage stereotypy especially, is an indicator of adverse health and is often now used as a measure of bad rearing conditions. And Alex asks, can I relate that to my own work? The answer is, I can only speculate, but there are a number of studies, both of the form you just mentioned, but physiological studies, suggesting that high levels of stereotypy indicate adverse health. Too steady a heartbeat is bad. Variable heartbeats indicate better health than too stable a heart rate. Same thing with a variety of brain waves. There is something inherently healthy about some aspects of variable physiological processes. Thus, perhaps one could assess the well-being of an animal by seeing what's the level of variability that can be reinforced. One could speculate further and suggest that maybe we could make animals healthier and happier by explicitly reinforcing higher levels of variation. But that's pure speculation. Thank you very much.